Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, we're back to discuss the fifth problem in the third homework set. Fifth problem is, again, it's a VEDA simulation. It's just trying to ask a few questions to make sure that the VEDA simulation that you perform, you're capable of interpreting the results. In this particular case, we're going to focus on the DMT contact model. So that would then have to be selected as the contact model used for this particular simulation. We're just going to simulate the force that the tip experiences as the distance d is systematically decreased, and when the tip comes into contact with the sample, we'll then use the DMT model to describe both the indentation and the forces that the tip experiences. So the input parameters in this calculation are specified in the homework set. We're picking a radius of the tip of 10 nanometers. We're using the modulus of the tip, in this case, to be 130 gigapascal. The modulus of the sample we picked is 100 gigapascal. The Poisson ratio of the tip and the sample, or typical values, 0.3, nothing special there. The A0 we selected, I think this is the default A0 in VEDA. It's about 0.2 of a nanometer. And then in this particular simulation, we chose to specify the Hamacher constant. So that has to be specified in the process of selecting the input parameters for the DMT model. And for this particular simulation, we picked the Hamacher constant of 1 × 10 to the minus 19 joules. When you press the simulate button with these input parameters, you'll end up with a graph. The graph that you get spans a much wider range of D values than are necessary to answer these questions with any accuracy. So what I did is I went into the calculation that VEDA returned, and I zoomed in on the particular region of interest. Particular region of interest, of course, is the region where the tip comes into contact with the sample. So when you zoom in on that region of interest, you should see a curve that looks somewhat similar to this. And from the data points on this curve, you're then able to answer these questions, hopefully in a very straightforward fashion. The answers to the questions can be facilitated by using this cursor positioning. So there's a crosshair cursor that you can use your mouse to position over any point in the curve. When you position the cursor over that point in the curve, a little box pops up, and the box then tells you the coordinates X and Y for the point that your cursor is located. So there's an example. The first question asked is, what force does the tip feel when the separation between the tip and the sample is 1 nanometer? That can be answered very nicely, very easily by positioning the cursor until the 1 nanometer position for the X coordinate lights up. When you get the cursor positioned properly, you'll find that the interaction force is about 0.17 nanonewtons. That's an attractive force, right? It's attractive because the force is less than 0, and when the force is less than 0, that's indicating that the tip is being attracted towards the substrate. So I think the correct answer for that is B of the choices given in the statement of the homework problem. I think the correct answer is B. Second question is, what is the largest attractive force that the tip experiences? Well, the largest attractive force would be the force located right here at the minimum of the VEDA simulation. Again, you can position the cursor there and you can read off the force, and the force is about 4.2 nanonewtons. Again, it's attractive because it's less than 0. Right? And of the choices given, D is the correct choice. Next question is, what is the indentation that results when the force is equal to 5 nanonewtons? So again, the cursor has to be positioned so that the cursor position is equivalent to 5 nanonewtons, or close to. It may not be exact, but it's close to 5 nanonewtons, right? The indentation is then going to be measured with respect to the point at which the tip just contacts the sample, right? So that's this position right here. And so you then have to measure the difference between this point and this point in order to find out how much the tip is indented in, how much the tip is indented into the sample. That's the deformation D, or the indentation. When I do that, I get 0.07 nanometers. And the correct answer for the choices given is A. The fourth question asks, what indents in this problem? I mean, does the tip indent into the sample, or is the tip crushed when it comes into contact with the sample? To answer that question, you have to look at the relative values for the Young's modulus of the tip and the sample. And to a very, very good approximation, these two Young's moduli are about the same. And so that means that both the tip and the sample are going to suffer some deformation in the process of indenting. I think the correct answer here is C. To a first guess, both tip and sample are deforming. If the sample modulus was much less than the modulus of the tip, then clearly the tip would push into the sample, but that's not the case here, right? And then the last question is, just before contact, right, as the tip comes into contact with the substrate, how does the force vary with D? So the way I answered that question is I went in with the cursors, and I just wrote down the values of the forces for different values of D. And then once I had a few data points on this curve for force versus distance, I was able to make a very simple plot. And from that plot, I was able to convince myself that the force varies as 1 over D squared. So I did that empirically from the actual simulation. Another way to answer this question is refer back to the second week, the start of the second week of lectures. We showed that the force interacts, a spherical tip of radius R tip interacts with a sample as 1 over D squared. So if you remember that result, you can just immediately write down what the answer is. And I think the choices given, D is probably the correct answer. So that's how I think about problem 5. It's designed to make sure that you can go into VEDA, do a DMT simulation, and then read off various parameters from that simulation to answer a variety of different questions.